Hello and welcome to Pep Talk with me, Mr. Pepperell. In this episode, we'll be thinking about what do we actually mean when we say an appliance is powerful. By the end of this episode, you should be able to tell me what do we actually mean by power and how can we calculate the power of an appliance.
So here's an electric winch with a powerful motor, and we know that an electric winch transfers electrical energy into gravitational potential as it lifts up a heavy load, and obviously it wastes some energy as well because some of that energy gets turned into heat energy and is wasted. But when I say it's a powerful motor, what do I actually mean? What am I talking about when I say power? Well, when I'm talking about power, what I'm actually talking about is the rate of energy transfer. So by talking about power, what I'm talking about is the energy supplied per second to an appliance. That's the power supplied to it, okay? And the more powerful an appliance is, the faster the rate at which energy is transferred by it. So to think about what this statement here actually means, the more powerful an appliance, the faster the rate at which it transfers energy, let's have a little think about this light bulb. Okay, now, if that light bulb was to transfer 1 joule of electrical energy into 1 joule of light energy every second, I would say that I had a 1 watt light bulb. Okay, watts is the unit of power, so 1 joule transferred per second, that's 1 joule being transferred from one type of energy into another type of energy, would make it a 1 watt light bulb. Now, a 1 watt light bulb wouldn't be very bright, you wouldn't be able to read by that, okay? So an electric light bulb, is typically a 60 watt light bulb is something you might have in your house, and that means that every second that goes by, every second you've got that light bulb turned on, that light bulb is transferring 60 joules of electrical energy into light energy. Now, quite often when we're talking about power and we're measuring something in watts, we're talking about quite big numbers, okay? So what we often do is we use something called a kilowatt, okay? And 1 kilowatt is just the same as 1,000 watts, the same as a kilometre is 1,000 metres. Quite often we'll talk about power measured in kilowatts, okay? And you'll note there that the unit, the watt, is given a capital W and a kilowatt is given a kW, small k, big W. So hopefully we can now understand what this statement means. My 60 watt light bulb here is transferring 60 joules of electrical energy into light energy every second, whereas my more powerful 100 watt light bulb is transferring 100 joules of electrical energy into light energy every second. So it doesn't take quite as long for it to transfer more energy. So the more powerful the appliance, the faster the rate at which it transfers energy. So now we know what power is. How do we actually calculate it? Well, like I've just said, power is amount of energy supplied over time. So the calculation to work out power is energy divided by time. So as long as we know the amount of energy supplied to a device that we can measure in joules, and we know how long it takes to supply that amount of energy, always measured in seconds, we can work out the power of the device measured in watts, and we can simplify that formula there just to P equals E over T. Okay, we've got capital E for energy, lowercase t for time, and capital P for power. So let's see if we can do the math on this one. Okay, my question says a motor transfers 10,000 joules of energy in 25 seconds. What is its power? So how powerful is the motor? Well, it's a simple case of using our equation. I'm just going to divide the amount of energy supplied to the device by the time it takes to supply that energy. So I've got 10,000 joules, 10,000 joules. It takes 25 seconds to supply it, 25 seconds. So 10,000 divided by 25 gives me a power of 400 watts. Or I could also give that in kilowatts. That would be 0.4 kilowatts. These two figures tell me exactly the same thing. Now, the important thing to remember when you get an exam question on this topic is that your time must always be given in seconds there, okay? Quite often in the exam they'll say, rather than energy's delivered in 25 seconds, they might say in 2 minutes. So you need to remember that there's 60 seconds in a minute and 2 minutes is 120 seconds. So always make sure that this figure is given in seconds. So let's just finish by thinking about what wattage actually means in the real world. We'll look at a couple of different devices here. Don't worry about noting these down. This is just to give you a bit of a frame of reference, really. Okay, and we'll start by thinking about our normal little torch there. Okay, and that is a 1 watt device, which means that every single second that torch transfers 1 joule of chemical energy from its batteries into electrical and then into heat and light energy. If we go over to the cooker over here, slightly bigger, it's a 10,000 watt device there, or a 10 kilowatt, which means 10,000 joules of energy being transferred every second. Our railway engine down here, we're getting bigger numbers now. This has got 1 million watts, which means 1 million joules of energy being transferred every second. We can also write that as 1 megawatt. Mega means a million, so this is actually a 1 megawatt piece of machinery. So a megawatt is a lot of power, but we can get a lot more powerful than that railway engine there. This is the Saturn V rocket that was used in the Apollo missions, which went to the moon back in the 60s, and the rocket engines of that were 100 megawatt machines. Okay, they transferred 100 million watts of chemical energy from the fuel into heat and light every single second. Okay, but even that is nothing compared to the average output of your average power station, which is 10,000 megawatts. That's 10,000 million watts of energy being transferred every single second by a power station. But it gets even more powerful than that. Here is the planet you live on, planet Earth, okay, and the energy demand of the planet Earth every single second is 10 million joules of energy need to be transferred every second. So our planet is actually a 10 million megawatt planet. That's how much energy we need to transfer every single second. But that's not the biggest wattage in our solar system. So here's our local star that we call the Sun. Well, what is the wattage of the Sun? What's the rate at which the Sun transfers energy? Well, it's a big number. In fact, if we have a little look here, we can see that it's a 1 with a lot of zeros after it. That's actually what that number says. It's actually 100 quintillion megawatts. Okay, that's a 1 with 20 megawatts, which of course a megawatt is a million watts anyway. So that's 100 quintillion million watts. That's the power of our local star, the Sun. That's the rate at which the Sun transfers energy.
So that's everything we need to know about electrical power and how to calculate it. Any problems with that at all, don't hesitate to tweet me at Mr_Pepperell or email me and I'll get back to you ASAP. Thanks for stopping by.